In this demo, we will implement support for an additional state, gold state. An account gets gold status when the balance is higher than 1000. We also need an extra rule for demo purposes. So let's say that when you have gold status and you deposit money, you get an immediate interest of 10%. I think this is the type of scenario we all wished would exist in real life. Nevertheless, it's a nice scenario that will allow us to see how less conditional statements are required. And let's make it a bit more complex. You can transition from gold to regular or overdrawn, and from regular to gold, but you can never directly transition from overdrawn to gold. You will need to be in regular status for at least one deposit. That means that the rules are a bit more complex than just looking at the balance. You can be in regular status even when you have a balance of more than 1000. Alright, let's implement this scenario. We start with adding the gold state class. It derives from bank account state, which means we should implement the deposit and withdraw methods. And just as with the other concrete state implementations, we're going to add a constructor that accepts the balance and bank account and sets them. The deposit method is easy. We're in gold state, so that means that when money is deposited, we get 10% interest applied immediately. So no conditional statement is required here. We simply add 10% as we are already in the gold state class. We don't need to check the status. In the withdraw method, we do need conditional statements to potentially transition to the two other states. So what we're saying here is that you can go from gold state to either regular or overdrawn state, depending on your account balance after you've withdrawn money. We also need to make a small change to our regular state, as you can potentially transition to gold state from regular state when depositing money. So, if the balance is over 1000 or equal to it, we switch to gold state. Another rule we wanted to implement was that you cannot transition from overdrawn to gold directly. You'll at least need to be in regular state for one deposit. And this rule is remarkably easy to implement. We don't have to change anything to our codebase, as our overdrawn state object only implements a transition to regular state. All that's left is adding a few additional statements for testing to our program class. First, we're gonna deposit enough money to get to gold status. Then we check whether that's indeed the case, and then we try and go back to overdrawn status. After we deposit more money, we should transition to regular instead of gold, and we can check for that by doing a deposit of 100. Let's give this a try. The first three statements are the same as in the previous demo. Then we're in overdrawn state and we deposit 2000. That means we now have a balance of 1800. So we switch to regular state because we can't directly switch to gold state. When we deposit 100 while in regular state, we move to gold state because our balance is now 1900. And when we withdraw 3000 from 1900, we automatically go to overdrawn state. And when we're in overdrawn state and deposit 3000, we have a balance over 1000, but because of the rule that we cannot immediately transition to gold state, we remain in regular state. So these are already quite complex rules. But all we had to do to implement all of this is create one new subclass and change the transitions. We didn't have to change the bank account class itself, and we didn't end up with as many conditional statements if we would have worked with an enumeration property for state on the bank account class. Even our rather complex transitioning rule was easy to implement. Let's have a look at the use cases for this pattern. There's two good use cases for this pattern. The first case in which you should consider this pattern is when an object's behavior depends on its state and it must change its behavior at runtime depending on that state. That's the use case we just implemented with our bank account example. Another good use case is when your objects are dealing with large conditional switch or if statements that depend on the object state. For example, by storing the state in an enumeration field on the object. Also not unlike our use case. This often results in several of your object operations to contain the same conditional structure. That's what we would have ended up with in our naive implementation. By using the state pattern, each branch of the conditional is put in a separate class, which lets you treat the object's state as an object in its own right. It can thus vary independently from other objects. Let's have a look at the pattern consequences. This pattern localizes state-specific behavior and partitions behavior for different states. We saw that, as all the behavior associated with a particular state was put in an object of its own. This works towards the single responsibility principle from the solid coding principles. Another positive consequence is that because state-specific code lives in a state subclass, new states and transitions can easily be added by defining new subclasses. We saw that when we extended our example with a new state in the second demo. That's the open-closed principle from the solid coding principles at work. But this can have a possible negative consequence as well. As the pattern distributes behavior across different state subclasses, the number of classes is increased, which adds additional complexity. But seeing long conditional statements are not desirable, this becomes more of a positive consequence than a negative consequence once the amount of state subclasses is large. Let's cover the related patterns next. There's a few related patterns. The first one is the flyweight. When you implement the state pattern without instance variables in the state objects, you're essentially making these state objects shareable, which makes them flyweights. There's also a relation to the singleton pattern, as state objects often are singletons. Strategy, bridge, and state are all related and look similar because they are based on composition, but they solve different problems. Let's have a look at the module summary. We learned about the state pattern in this module. Its intent is to allow an object to alter its behavior when its internal state changes. If you find yourself in a situation where you have an object which can have different states and you're currently storing an enumeration on that object, which you then use inside that object to modify its behavior depending on that state, well, then this pattern is a really helpful one to look into, in my opinion. As far as implementation goes, remember that it's in the state objects themselves that the transitions to a new state are handled. That means that each state object needs a reference to the context class. What's also important to remember is that requests on the context that either need to take state into account or can result in state transitions are handled by the state objects. So the context needs to pass these requests through to the underlying state objects to handle them. That essentially means that you need methods to handle these requests on the abstract base class. Up next is the iterator pattern, something you use every day.